Hi guys, Rito here. Today, since the other session I couldn't cover the chair projections and kind of the Newman projections of chairs, I thought I would cover it here in a separate video. And also we're gonna do some of resonance and kind of electron pushing and kind of the rules of resonance and kind of what to look for in a resonance structure. Um, so to start off tonight, I guess we're recording this at 9:30 p.m. Um, kind of what are Newman projection? What are chair projections, first of all? So, chair projections are a way of visualizing any kind of cyclocompound, particularly cyclohexane. We'll see a lot in this class. Kind of how they look in 3D space and why different groups have different interactions with the ring. So, if we look at a normal cyclohexane. We don't really see a lot about the structure. We don't know how, we just look at it on a 2D space. And we know molecules are 3D. So how do we translate a 2D structure into 3D? Well, there's two things we have to remember. Is that carbon is a tetrahedral shape, so it's not just a flat ring molecule. And because of the tetrahedral shape, there are going to be specific ways that groups are going to be laid out on the ring compared to where that carbon is. So the way that we draw kind of these 3D structures is what we call the chair projection, which basically the molecule is going to sit like a lawn chair, essentially, where they have kind of this shape to it. It's not perfect. Um, it's typically just a bunch of parallel lines going the same side, but this should be fine for the purposes that we'll talk about. And so we just have to find out, okay, on this shape, what are the ways that different groups can be laid out? And chair projections have a kind of alternating pattern to them, where if you're going up and you see that this kind of vertex is going up, then one of the groups is going to point straight up. And if it's going down on the vertex, then it's going to go straight down. These straight up and straight down are what we call axial. These are the axial positions. Now, on one carbon, because it is tetrahedral, no two groups can be sent pointing the same direction. So if one axial is up, then the other group has to be pointing down. This is our equatorial position. And you notice that when I start drawing the other kind of groups on this, you'll see that we see a alternating pattern, where axial up is then next to axial down, equatorial down is next to equatorial up. So you see that each carbon kind of flip-flops their pattern, where it goes up, then down, down, then up and down and up. So this is how chairs are, this is their general pattern. This is how the groups are going to be laid out on the chair. Now, they are 3D space and molecules don't sit still. So there is a chance, and actually, they actually do this thousands of times per second, is that they flip. They'll start, flipping between their two chair conformations. So how do we draw the chair flip? We basically just have to reverse the sides or kind of just flip on how they're facing. So kind of like that. And it flips the chair, however, the same pattern doesn't change. So you still have down and up and down and up and down and up and down. So they flip. It just flipped. And in fact, a way to see kind of what carbons they are, let's start by numbering the 2D carbon, the 2D cyclohexane. So this is carbon 1, 2, 3, 4, 5, and 6. So I'm going to number it, and the carbons, no matter the number, they're going to keep the same number, alright? I'm not going to change, this carbon 1 is then going to become carbon 2. No, the carbons are going to stay the same number. The same number means the same carbon. So if I were to pick this first chair, I'll just label it going clockwise. 1, 2, 3, 4, 5, and 6. With chairs, when they chair flip, the number is then going to rotate one clockwise. So this one was in this, top right corner. Now it's going to be in this bottom right. So 1, 2, 3, 4, 5, and 6. So they rotate one clockwise. These numbers are arbitrary. You can start from, if you want to start putting number 1 here and then go clockwise, that's perfectly fine. Just you have to keep it consistent with all of your numbering. So our next point kind of now is that we don't just look at, cyclohexane. It's kind of it's a basic molecule. So we're going to start adding groups onto it. Let's take a methyl group. Let's take a methyl group on there. Let's say now we want to draw. I'll move the camera over a little bit, see where we're going. Let's say now that we want to draw a methyl onto this carbon 1 right here. Now, because they can be pointing up or down, the groups are going to be specified now on a 2D structure if they're up or down. I'll draw 2 methyl groups on this molecule just to showcase. One methyl will be having the wedge, and another methyl will be having a dash. Those are the 2 ways that they can be represented, and basically, wedges mean that they're pointing up, and dashes mean they're pointing down, right? Wedges are towards us, dashes are away from us. So naturally, the dashes are going to be down, and the wedges are going to be pointing up. So now we're going to translate this into our chair to look at our molecule in 3D space. So we'll draw the first chair there. And we're going to number this 1 and 2. We're going to number our carbons. So let's just number 1, 2, and 3. And let's pick 1, 2, and 3. So remember that they always follow our pattern of up, down, down, up, and they always reverse. So on carbon 1, our methyl is pointing up. This vertex is going up, so that means that we must have an axial up. And then what isn't labeled is hydrogen, so down would be our hydrogen. Carbon 3, our methyl is going to be pointing down. So if you look at our groups, we can't have the methyl pointing up in the axial position. So it has to be in the equatorial. And our hydrogen will be pointing up. Okay, so awesome. Now we gotta look at this and say, okay, if we were to put our eyes straight down, let's say bonds 3 and 2, what does our Newmann projection look like? Well, we know our hydrogen is going to be pointing up. So the first line that we're going to draw is the up. And because the hydrogen is pointing up, we're going to have the upside down Y. So if I'm looking down this bond, and my hydrogen is pointing up, and my methyl is facing down, if I were to face the camera, and I'm, the bond line between us, hydrogen has to be pointing up, and because of the ring, our metal has to be pointing away from the ring. So it has to be pointing to, I guess, your right? Yeah, this right. So our hydrogen's pointing up, metal's pointing to the right, and our ring carbon is to the left. Obviously, when you get your model kit, you can kind of see that. I'm going to put RC for ring carbon. So now, our bond 2 is going to be looking at the back carbon that we're looking at, and we see that because this is pointing down, this axial has to be pointing down as well, and then the equatorial up. So because it's equatorial up, it has to be pointing away from the ring, so our hydrogen is going to be here, and your hydrogen is also pointing down. Therefore, our ring carbon must be pointing to the left from our back carbon. So here we can see we're kind of looking at the interactions between this methyl group and the ring carbons. That's what we care about, is the methyl group, or any other group that would be here, and interactions with other groups on the ring, and also the ring itself. That's what we're looking for. So because a gauche interaction means that it would have to be 60 degrees, so either in this position or this position, there are only hydrogens here, so we don't count those interactions. The only interactions we really care about are that this methyl group is a complete 180 degrees to this other ring carbon, meaning that it's anti. So this has no interaction with the ring because it's anti. So now let's picture a different way to look at this. Let's look at the ring looking at the axial methyl. And so we're going to put our eye here. To really see how this Newmann projection is going to look out, let's draw the other bonds here. Hydrogen is pointing down, also hydrogen is pointing up. So if we look already, we can kind of see our Newmann projection already. So let's draw a Newmann projection down below. So it's, yeah. Our hydrogen is pointing down. Hydrogen is pointing to the left, and our ring carbon is pointing to the right. Draw the back carbon. So on this carbon, we have a ring carbon pointing down and to the right. Our methyl group is pointing up. And we have a hydrogen pointing down. Okay. So now we see that we have a gauche interaction between the methyl and the ring carbon because they're right next to each other. They're 60 degrees. So we have one gauche interaction here. Now, if I were to put my eye looking, and I'll put it to red, if I were to put my eye down bonds 1 and 2, carbons 1 and 2, I would get a different projection, and I would see that I would also have a different gauche interaction with another carbon in the ring. So let's draw out the Newmann projection. Our methyl is pointing up, and our hydrogen is pointing down and to the left. Our ring carbon is pointing down and to the right. Let's draw the carbon 2 in the back. We have a hydrogen pointing down, a hydrogen pointing up and to the left, and we have a ring carbon also pointing up and to the right. So we see that we have a different interaction with a different ring carbon. that ring carbon is the one I'm going to circle in red. That is the gauge interaction. And the carbon I'm going to circle in black is the first gauge interaction that we have. So looking here, we see that the axial group has 2 total interactions with the ring. And this kind of plays into the rule that Professor said, where an axial group is always going to have 2 gauge interactions with the ring itself. So automatically, you're going to count, when you have an axial group, you're automatically going to see, oh, I'm going to have 2 gauge interactions with the ring itself. Good to know. And if you're wondering about naming 2, because these 2 methyl groups are pointing in a different direction, this cyclohexane is going to be called trans 1,3 dimethyl cyclohexane. So let's look at another ring where metals are kind of next to each other. Let's say we did trans with a different one, so let's do a cis isomer. So let's say we're given cis 1,2 dimethyl cyclohexane. Now, a big tip I would give is that I would draw the molecule in 2D space first. Draw it in 2D so we can translate it to 3D. So let's draw a cyclohexane. And let's say this is 1 and this is 2. Carbon 1 and carbon 2. Okay, so now we just need to draw a chair conformation of this. So we're going to translate this into 3D. Okay. Let's call these 2 carbons 1 and 2. Now, because they're pointing up, one of them has to be axial up. And it can't be in the axial position, the other carbon, the other methyl group on 2, because that axial is down. So it has to be equatorial up. So let's draw our other bonds that we have. And let's look down, bonds, carbons 2 and 1. So from this, we can kind of already see our Newmann projection. Our hydrogen's pointing down and our methyls pointing up and to the right. And the ring carbon is up and to the left. Look on a little bitty circle. If you look on carbon 1, our metal is pointing up. Hydrogen is pointing down. And we have our ring carbon. Okay. So now we gotta look for gauge interactions. What's 60 degrees to each other? Well, we have the up methyl, or the methyl on 1 is gauge to the ring carbon. This ring carbon specifically. And we see that the methyls are actually gauge to each other. So in this one conformation right here, we see that we already have 2 gauge interactions. If I were to chair flip it, then it would probably be the same thing. Call that 1 and 2, because we just rotated it clockwise. Our metals pointing up. Our metals are pointing up. So even when we chair flip it, if our metal was up, it's going to stay up. So no matter if we chair flip it, if the group was up, it'll stay up. If it was down, it'll stay down. So let's put our eye here. Draw the Newmann projection of our chair flip. Our hydrogen is pointing down. Our metal up and to the right. Draw the back carbon. Our metal's pointing up. Hydrogen pointing down. And our ring carbon. Oh, I flipped it. I flipped the metal, the first metal in the ring carbon. Our metal should be here for our first one. Yes, that looks right. Another common pattern you'll see is that typically the ring carbons are kind of on top of each other. That's a common pattern you'll see when you're talking about cyclohexane chairs. So let's look at this. We still have 2 gauche interactions even after our chair flip. So what does this tell us? Well, axial is always going to have gauche interactions. And if they're cis, they're still going to be, if the metals are cis, they're still going to have that gauche interaction with each other. Because they're always pointing up. So that's how chair conformations kind of work. Some good practice you can have is kind of just drawing cyclohexane and putting some different groups on there. Maybe like a methyl on 1, a methyl on 4, an ethyl on 2. Talking about stability, actually now, because axial always has 2 gauche interactions with the ring, that means that it's putting more energy on the ring. It's making it more unstable. The more gauche interactions, the more unstable it is. So the most stable conformation of a chair is going to be one that gives the least amount of gauche interactions. And so let's talk about, let's bring another example. A perfect example of this would be something like a trans 1,4-dimethyl. Or trans 1,2. Let's do that. So we're going to draw the chair. And one methyl is going to be pointing up. And one methyl pointing down. So because we use our rule of, let's actually draw the Newmann projection of this. So our methyl is pointing down, hydrogen up and to the right, and the ring carbon to the left. Okay, so in this way, we have 2 gauche interactions. The methyl the metals have one with the ring. So we're going to have two Gaussian interactions here. If we were to chair flip this, and let's rotate it one clockwise. So this was down, this would be up. And since this was down, it'll stay down. So let's draw a Newmann projection looking down these two bonds. I think I've done it again. Front carbon. Oh yes. This metal goes here. This metal goes here. This is a hydrogen, and these two are ring carbons. So what do we see now? Well, when our metals are in the equatorial position, then that means that they have no more Gaussian interactions with the ring. They just have one by themselves, right? This is just one Gaussian interaction between the two metal groups themselves. So which one is more stable? Well, we know this one has 4 Gaussian interactions. This one only has 1. So the form that the chair is most likely going to be in is its most stable form. In this case, where both the groups are equatorial, this is going to be its most stable form, because it only has 1 Gaussian interaction, and this one has 4, even though the metals are anti to each other. So that's on chair projections and kind of how to see Newmann projections on them, and kind of determining about the stability of them, and also how to tell which one is most stable, which one is most unstable. Now let's go on to talking about resonance and kind of the kind of electron pushing rules that we want to use in this class. Alright, so let's talk about resonance and kind of electron pushing in general. So resonance is basically talking about where can a charge on a molecule kind of move around if it can. It's showing where that charge can, be delocalized somewhere inside of the molecule. Because there may be points where you'll see later in this class where resonance does play a big part in kind of reactions, which you'll learn about. So kind of where can that charge move is a big part of organic chemistry. So in order to understand that, we need to understand some of resonance and kind of some rules about resonance and kind of electron pushing. So there are two major rules of resonance. One is to never break a single bond. So you can't break a single bond during resonance, because resonance, you have to keep the same. It's the same molecule. It's just different in how the charge is located. So you're not gonna. So by breaking a single bond, you would be like making a different molecule, and that's not what resonance is. Another big rule is to never exceed the octet rule. So this only applies for second row elements like carbon, nitrogen, oxygen, the big 3 of organic chem. You cannot violate the octet rule of them, because they can't hold more electrons. So anything that is like pentavalent nitrogen or pentavalent oxygen or pentavalent carbon, you cannot exceed that because they cannot hold it. So I've written out some examples that we can try to look at and talk about. And the first 4 are kind of demonstrating the rules. So if we were to look at kind of this molecule and say, oh, we have some pi electrons next to a positive charge, well, why can't they move there? Well, if we draw the structure that we just drew, you'll see that we have created a pentavalent nitrogen, and that's not allowed because nitrogen cannot have more than 8 electrons. So this resonance structure is bogus. This is complete nonsense. That cannot happen. Okay, well, you know, what about this next molecule here? There's no, oxygen, nitrogen doesn't have 4 bonds here, so why can't we just move this alkene here? Well, a thing that you probably need to develop a skill for is seeing where are lone pairs. And so nitrogen is neutral here, which means it has 3 bonds and 1 lone pair. So if you were to draw that structure, you again would have nitrogen with 4 bonds and a lone pair, which means that it's exceeding the octet rule. It can't be done. So that's also nonsense. Be careful of that. For this one, this structure right here, we have a carbon that's positively charged, so it's missing some electrons. So can this alkene move here? And this resonance form would be valid. Because the carbon over here only has 1 hydrogen. It has an empty orbital that can accept electrons, which this double bond, when it moves over, can fill that empty orbital that needed electrons. And so now you're left, that carbon that did have electrons now has no electrons. So the plus charge would move to it, and this is a valid resonance form. Now let's talk about this bottom one. Well, there's a positive charge on that carbon, so can't I just move this bond here? No, you cannot. Because what did we just do? We just broke the first rule of never breaking a single bond. That is not a resonance form. That is a completely different molecule. So don't do that. I'm drawing resonance forms. So now we've gone over some of the rules and such. Let's go over some resonance forms, and I've written some examples here. And basically, resonance is about moving the charge. It's about moving the charge. So you have to preserve the charge inside of the whole molecule. If it was -1 at first, it's still going to stay -1 when you do all your resonance forms. If it was neutral, it's going to stay neutral. If it was positive, it's going to stay positive. So the amount of starting charge it had, that's the amount that it will have. So take a look at this first one. We have a negative charge next to an alkene, which means that there is a lone pair on this carbon. That's what a negative charge is. So if we were to move this negative charge to this carbon-carbon bond, we would end up with this carbon having 5 bonds. So how do we prevent that? Well, this double pair, this double bond, one of the bonds is a set of 2 electrons, which this double bond can move to the end carbon here. Which those 2 electrons that were in the bond now become a lone pair. So we've moved the charge around to the other side of this molecule. So let's look at the next example. This is a compound called aniline. And we see that nitrogen is neutral, so it has 3 bonds and 1 lone pair. So this lone pair can actually come down and make a bond. But when that happens, that double bond cannot stay there anymore. It has to jump ship. It has to make a lone pair. So you draw a double bond with nitrogen, and nitrogen now becomes positive because now it has 4 bonds. And this double bond then became a negative charge. So we preserve charge because this whole molecule is still neutral. Now, this lone pair can move again because it's next to another double bond. So it can move down, and now these 2 electrons have to be kicked off to the other carbon. It's a little cramped, but we see that the negative charge is moved to the bottom carbon. Now there is one more, where the lone pair does form with these 2 carbons, and the double bond here gets kicked off. I don't have space to draw it, but it'll be basically the same thing as this top one, but kind of this lone pair would be on this side. And then that lone pair can jump to make a double bond and kick this bond back up to nitrogen, giving you this structure. So let's talk about this bottom one right here. And I'll move the arrow on it so it gets pointed down. But one thing to consider is that this COO is called a carbonyl group. Carbonyls have resonance, where one of the bonds in the double bond can move up to the oxygen. When that happens, oxygen then has 3 lone pairs, which becomes negative. If oxygen has 1 bond only and 3 lone pairs, it's going to have a negative charge. The carbon just lost electrons because the electrons went all the way to oxygen. So it's going to bear a positive charge where it was. Now, this double bond can move to that positive charge. It does have resonance with that because we see when that double bond moves to that other carbon, the positive charge gets moved all the way down to this carbon down here. But we still have a negative charge on oxygen. So what does that mean? Well, we have a negative and a positive charge. This molecule is still neutral, just like our starting molecule. Right? The resonance shows that the molecule stays neutral even when the charge leads to anions and cations. For this one, well, we see that we have a double bond next to a positive charge, next to a nitrogen positive charge. So we can't have resonance there. We can have resonance here. However, this bond is making, so a bond will have to break somewhere so that nitrogen doesn't become pentavalent. Where is one going to break? Well, we can't break a single bond between this N and this O, but there is a double bond here that could become a lone pair for that oxygen. And that's what's going to happen. The double bond here is then going to move to the oxygen to become a lone pair. So what do we get when that happens? And I'll draw it more up. We see that We have two negative charges on oxygen. We have a negative charge on both the oxygens. And we have a positive charge on nitrogen and the carbocation. That's where our carbon lost electrons. So that means that our molecule is still neutral, even with the amount of negative charges and positive charges it has. They cancel out each other, so they're gonna stay positive. The molecule is going to stay positive. So that is a valid resonance form. A common pattern we see is typically like a negative charge next to a double bond or a positive charge next to a double bond. They like to move between each other. So if we see this negative charge and next to a double bond, this negative charge can form a double bond with this carbon. Because that carbon can't be pentavalent, one of these bonds is going to have to move somewhere. Well, you can't move that single bond, but you can move one of the double bonds. And it's going to go to nitrogen because it can't move to the other oxygen or the other carbon because that's an sp3 carbon. It already is full. Nitrogen isn't. It can hold another charge. It can take, one more electron in its pi orbital. Oof, where's my eraser? I want to make that error a little smaller so I have more space to draw the molecule. So we form a double bond here, and since the nitrogen is gaining another lone pair, it's going to have two lone pairs. Meaning, it has two lone pairs and two bonds. It's going to be a negative charge. So we've moved the negative charge around, and we've kept only one negative charge in the molecule. The same deal is going to happen kind of over here as well. The negative charge next to this sp2 carbon can form a bond between these two. When this bond makes, it's going to kick off the two electrons in the double bond. It's going to go to the end carbon there. So that bond will form, and you have a negative charge here on the end carbon. So some other examples that we have over here are molecules with tons of resonance. The double bonds can jump all over the place in this molecule. So let's talk about anthracene for a second. This system is fully conjugated. All of the pi orbitals overlap, so all the double bonds can move to each other. So let's say we move this one to here. Well, this carbon can't be pentavalent, so one of the bonds will have to move. This bond, actually I should do it, yeah, let's actually do it that way. So that bond will move here, this bond has to move here, and this bond in the middle has to move over here. So now where can these electrons go? Actually, wait a minute. Those electrons wouldn't move like that. My bad. Instead, they're going to move like this. This middle bond can jump to this carbon. When it does, these bonds have to be kicked off somewhere. So this bond will go to the middle in the 2, and this bond will move here to this bond, because that carbon can have another bond. So if I draw it properly this time, I see that this bond, that middle bond moved to this carbon, this moved to the middle, and this moved down to the left. Wonderful. So we have another ring next to it. It can do the same thing. So we see that the double bonds have basically moved from ring to ring, right? Each ring will have a set of, double bonds in it. One set will have 2, and we see that, it it can move a lot. The electrons can move a lot. So let's take a look at the second example here. We have a pi bond next to a positive charge. That pi bond can move to that positive charge and form a bond there. When that happens, one of the carbons lost electrons. It wasn't this carbon right here, because it still has a double bond here. Instead, it's going to be this carbon, which lost electrons in the process. But there's another double bond next to it, which can move. So when we see that, this carbon didn't lose, and this carbon gained. But then this carbon at the end is going to lose electrons. So that's why the positive charge is going to be on the end. Now let's talk about this last resonance, where we look at a benzylic carbocation. Well, just like the examples before, we see a common pattern of pi bonds being next to a positive charge. When that happens, we see that they can make a bond. So we see that this pi bond can move to that positive charge. And remove that positive charge onto that carbon. Well, it can still move. There's still double bonds next to it. Like this double bond right here, it can move. So your positive charge there. Well, it can still move because it's next to another pi bond. So we see that we're going to have a lot of resonance. So here. And then now that positive charge can again move to its original spot because it's next to a double bond. And we're back to where we started, just the pi bonds are now between different carbons. So that's a little about electron pushing. Remember, with electrons and kind of resonance, you want to draw double-headed arrows, because each kind of head of that arrow represents an electron. So double-headed means both of the electrons in the pi bond or lone pair are moving. So the double-headed arrow is important. And another thing to keep in mind is just never exceeding the octet rule, and to never break a single bond. There are still some things. There is a question in your example quiz about, and I'll draw it over here. Where you were given this starting molecule, and then you were given 3 products: bromide, ethene, and carbon dioxide. And your goal was basically, okay, push the electrons to show how did we get these products. Well, let's think of it like a puzzle. We're given the start, and we're given the end. The way why we're pushing electrons is to figure out what happened in the middle. How did we create these 3 products? Now, this is a good example of this not being resonance. So because it's not resonance, we can break the rule of not breaking single bonds. The octet rule still applies. We cannot exceed the octet rule. So because we're creating different molecules, we don't have to abide by the never breaking single bonds. But resonance does. So that's a key difference. Resonance is never breaking single bonds. Pushing electrons in like a mechanism for a reaction or something like this would involve breaking single bonds because we're making 3 different molecules. So let's figure out what happened. The first thing that we're going to look at is that we have a negative charge here. So this is probably where it's going to start, right? This lone pair, oxygen doesn't like being negative, so these lone pairs are going to find somewhere to go. One of our products is carbon dioxide. So the C double bond to O 2 times. We have this C right here. So if this lone pair were to make a bond, I'll draw kind of like the bond forming in like a dotted line. So it's not there yet, it's just kind of forming. Well, that carbon is going to become pentavalent, and we can't have that. So, how do we avoid this problem? Do we push the electrons up here? No, we can't. No, we wouldn't want to do that, because then we're just creating a negative charge on the other oxygen. And we don't want that, because we'll get the same problem. So, the other thing is that we're making a C double bond to C. If we look at the hydrogens here, we see that we kind of have it, but we just need a bond between these 2 carbons, and then we need to break off this bromine somehow. So here, when this bond makes, this bond between this carbon and this carbon is going to break and make a bond between these 2 carbons. Right? We're breaking it off. This is becoming its own separate thing, and this is becoming its own separate thing. So when this bond makes, a bond has to break somewhere. We know which bond to break because we know that we have a bromide ion. So the single bond between carbon and bromine, the electrons in this bond are going to go back to bromine. When we break it, we see that we have separated this into our 3 products: our bromide, our ethene, and our carbon dioxide. So these electrons are good. One bond from the lone pair goes to make a double bond, and because the carbon can't be pentavalent, the bond between this middle carbon and the carbonyl carbon breaks, and that goes to form a double bond. Because of this double bond forming, this carbon at the end will become pentavalent. To avoid that problem, the bromine and the carbon bond, the electrons in the carbon-bromine bond are going to go to bromine. 1, because bromine is more electronegative, and 2, bromide is one of our products. So we know the electrons are going to go to bromine. But bromine is going to be more electronegative, meaning it's going to want the electrons way more than the carbon wants to have them. So the bromine will fall off to make bromide, the ethene will form, and the carbon dioxide will form. So that's resonance and electron pushing. Um, if you had any questions about any kind of resonance forms that you had, you can send them to me. If there's anything that you kind of need clarified or kind of want more of an explanation to, let me know. And good luck on resonance and electron pushing.